So, hi everyone. I'm really excited to tell you about a story that happens daily in front of VS Code and Vim sessions alike around the world. It's a story that begins with, could you change this one little thing, and is soon followed by many open tabs and a sensation of being overwhelmed. My goal for this talk is to equip you with the idea that having a map of your code could make the next telling of this story turn out a bit differently. But for you to understand how I became obsessed with the idea of code maps, you should know that I've always liked pictures of systems. When I was studying electrical engineering, I really liked the circuit diagrams and the state machines. As a data engineer, I drew out my data pipelines and my database schemas. Nowadays, I work on visualizing application infrastructure at Datadog with a focus on network topology. But in my free time, I like using React to play with new ways of showing old data. So to give you a small example, these are all the trains that are active in the New York City Metro North schedule at once, based on something that was done for 19th century France. And since New York City's train schedule is busier than 19th century France, I added some filters. I also like making art with the data that we leave behind as we do our work. So when interns join our team, before they go, I make visualizations with their GitHub data and their Trello cards. So if you're interested in this, you should talk to me later. But on to the topic of my presentation. I gave this talk a cheeky title, not because developers frequently fall down while typing, but because falling is disorienting, and being disoriented is a familiar feeling for us. It happens all the time when you join a feature that's undocumented, or you install a new library and you want to see what's happening inside. Or say you're on call, that routinely throws you into areas of code that you've never been in before, but you need to understand that quickly. This can even happen with files where you are supposedly the expert because it's been a little while. So I want to think about what we do when we're lost in the real world. First, we wander around. We look for landmarks or signs that help us orient us to find something familiar. If people are nearby, maybe you can ask for directions, and hopefully it's a local and not a tourist. The best case scenario is if you have a Maps app on your phone, because that tells you both where you are and gives you a path to where you need to be. Let's compare this to the code experience. In the code world, we also wander around, but instead of walking, it looks like scrolling through files, looking for important names and Control-Fing for them. Maybe you'll even find a comment. You can also ask for directions, right? You can use git blame to find who changes this file. Maybe your repository has a code owner's file, and you can Slack somebody, and hopefully it'll work out. But if we think about what a map means for code, in my experience, this is much more nebulous. If you're lucky, maybe somebody made a flow chart early in the project's history, but it's really a luck thing many of the times. So this talk was born from a desire to make reliable code maps a viable alternative. So there are hundreds of definitions of map, many of which focus on the fact that we're talking about real land. So I picked one that suits our needs. I'm just calling a map something that gives us a graphical way to think about code spatially. If we're going to use maps well, we have to come to terms with the fact that they are abstract by design. The only way to capture every single detail would be to look at the code directly. To be useful, maps must leave information out, and this is considered a feature and not a bug. Intentional information hiding is a super familiar concept in systems engineering. So let's see how this applied to a real map design decision. When Massimo Vignelli spent 8 years redesigning the New York City subway, he made this crisp schematic map. It focuses exclusively on the information that you need when you're underground and leaves out all the details about where streets are above ground. Now, many people like this design. It's really clean, but it's not the map that the MTA uses. This is the map that we use. It conveys information about what's happening above ground, and it reveals that the subway does not only have 45-degree and 90-degree turns. And you might be asking, which map is the right map? I would say that it really depends. More information is not helpful if it's irrelevant to what you're trying to do. So a good design will prioritize what's relevant to a particular user. All of this is to say that the ideal abstraction level is going to be situation specific, and usefulness depends on what you're trying to accomplish. With that in mind, today we'll focus on the information that you need when you're making a code change. Whether you're adding a feature or fixing a bug, having a map can highlight the information that's most relevant to your task at hand. One thing I'll add is that it's not just about getting to a destination. A good map gives you information that you didn't ask for, but helps you get to your destination safely. Think about where the dragons in your codebase are, whether that's a module that depends on a global variable, lines where reordering sneakily changes behavior, or just an area of code that has 0 tests. So our plan for today, I'm going to look at some lessons from the past in academia. I'm going to show you some tools that you can use right now, and I'll show you some experiments that I tried with adding more interactions to the tools that exist already. So in preparation for this talk, I spent a few weekends reading different papers about tools that support developers as they change code. I wish I could tell you about all of them, but there's one that really resonated. To contextualize this, I'd like to repeat an objection that I frequently heard when I told people about this idea of code maps. They'd say something like, that sounds nice. This project had an architecture diagram at the start, but then we built it differently, and nobody changed it. And these diagrams never get revisited, partly because an incomplete or a misleading map is worse than not having one at all, because your mental model is what's used to debug. So this paper is from 1995, and it addresses that question head on. It proposed a technique that was used to help refactor the Excel code base. This graphic shows some of the papers that it influenced through 2004, because that's where the visualization tools database ended. And while it was originally done with Java code, the approach can be generalized. So I'm going to step you through it. The technique is called reflection. So first, you take a concept model, which is very similar to the diagrams that you already may have seen before. Next, you take each one of those nodes in your diagram and link them to specific files in your code base. Then you'll use some sort of language-specific tool to get the automatic dependencies between the files in your code base. And then we're going to combine all of them. Now, this was a little bit abstract, so I'm going to walk you through a couple examples. Before I do that, I just want to highlight why this is such a big deal. Because the gaps between what is in your mental model and what is in the code is where the bugs are. When you think that two things are connected, but they're actually not, that's how you get strange side effects happening. So this is from a paper that Professor Murphy gave a number of years later, but I used it because it had color. On the left was the plan, and the right highlights the differences. There's a lot going on here, so I've made a small React example to show how this can be useful. So I'm taking a familiar React pattern, the container, view, behavioral, presentational pattern. So we have a view component, we have a container, which does some business logic, and data API, which is intentionally vaguely named. These are the code. This is the code that might try to implement that model. So here we have a small data API. We have a super minimal view component. We have a container component that takes the data API and puts that data into the view component. The second step was to do the mapping. So I made some regular expressions that associated each one of those files with a block in my concept model. And then I ran Madge, which is a tool we'll hear more about later. And because this was the start of the project, everything is as expected. There are only matching edges. Now, a couple sprints pass, and some features were added. We wanted to get some people data. Somebody told you they refactored something, and all your unit tests still pass. So maybe nothing strange happened. These are the changes. They're not super important, but you can look back at them later. And we can see that after going through the reflection process, there are some differences. There's an import edge that we didn't expect, and something that we thought would exist has disappeared. So what do we do when we see this diagram? Well, most of the problems originated from the data API node. And it opens a conversation to what exactly does it mean to have a data API? Is it just for network requests? Is it for transforming your data? There isn't a right answer per se. You can move your functions around, or you can rename your task node. But either way, something has to be done to realign your mental model with the code. Now, that was a really small example, but this technique is especially useful when your system has many pieces and many files. Since the first step to solving any problem is knowing that there is a problem, having a diagram that shows exactly where your goals differed from reality is very convenient. So if we come back to our original question that this paper was tackling, there are two main takeaways that I think we can use. One is that when we think about synchronizing the plan and the code, Neither one is necessarily right because the needs have changed over time. What this tool does is highlight those differences and not focus on which one is correct. And it gives us a clear visual guide to determine where we should update our code, our plan, or possibly both. Secondly, I think this approach is unique because it combines the human capacity for reasoning about abstract concepts with the thoroughness of a machine search. So we solve the problem of out-of-dateness with hand-drawn diagrams, and we solve the problem of we've shown everything, but it's chaotic. That comes from fully automatic tools. So when humans and computers are good at different things, reflection embraces that difference and lets each party focus on their respective strength. So now we're going to jump forward in time 24 years and examine some tools that we can use right now in the JavaScript ecosystem. So one way to think about this might be to use a language that looks exactly like our visual plan, because two things can't diverge if they're exactly the same thing. This is an approach that's used in signal processing and many visual programming languages. We'll take a look at the second category because they're more fun. So MaxMSP is one of the oldest programming languages. Each block can be a source of sound or something that transforms sound. And it's very intuitive even for non-programmers to figure out how to make new types of audio with this type of interface. There's also Mimo, which is a web app that you can try, and you can do all sorts of fun things with 2D graphics on the web. There are tens and tens of these tools. The last example I'll show shows that you can also do this with 3D graphics. This is very popular in the creative coding community. Now, while these languages are fun to work with, we're here and we're writing our JavaScript applications, so we can't use those quite yet. So we're going to change our question once again. And we're going to focus on what tools we can use that generate visualizations from our existing code so we can put them into CI and other automated systems. It turns out there are a lot of tools out there, and many of them are shaped sort of like a directed graph visualization using nodes and links. Now, directed graph just means that our edges have a direction, and when we say it's a DAG, that just means that there's no self-loops. And anytime we draw an edge, we just mean that some node A uses another node B. But this leaves us with one open question, which is, what do we want our nodes to be? What is the unit of our map? We don't have to pick just one thing, and we can lean on the mapping world to help. Consider how we define political bodies. There's a spectrum of abstraction going from continent all the way down to neighborhood, with many steps in between. And it's not helpful to worry too much about the size of these things when creating the ladder, because even though states are smaller than countries, the United Kingdom fits into Texas. So similarly, when we're looking at our nodes in code, I wouldn't worry too much about whether a class fits into one file or it's split into 4 pieces that got imported into a root component. It's really the conceptual boundary that matters. So to guide our tour, I've made a ladder of abstraction which we're going to descend, and there's a small detour for state because it doesn't fit well. So the first of these nodes is to first of these categories is to use files as our nodes. All of these, at each stage of the ladder, the question is basically the same. If I change one node, which other ones will be affected? The first is ARKit. ARKit as in architecture and not augmented reality. It builds a straightforward module dependency graph. It works with TypeScript and Webpack. You can look it up online. It gives you an ability to group your nodes with custom conceptual groups. Here at the bottom, we've grouped all our NPM dependencies together, but you could also do things like group all your client and server files. There's another tool called Dependency Cruisers. So say you don't have time to create custom groups for your components, and if your project structure is very disciplined, then maybe your folders make sense as conceptual groups. And Dependency Cruiser lets you reuse those. The last tool in this category that I'll show is Madge, which adds the innovation of coloring your nodes based on their properties. So here our leaf nodes are green, and it has an extensible API, which means we'll see it again in our feature section. So the next rung of our ladder is to think about our nodes as functions. And you've probably seen a call graph before inside our devtools. So a dynamic call graph is generated at runtime, and it shows a single path through your tree. And they can be very helpful for knowing how two distant functions that really don't seem like they should be related somehow end up calling each other. However, there's another type of call graph which shows a bigger picture. and this is called a static call graph. And they attempt to show approximately all possible ways that functions can call each other. Now, you might notice this example is from Python and not from JavaScript, and that's because this is a really difficult area of computer science research. Because each language treats things like dynamic dispatch differently, it's been hard to do for JavaScript before, and I couldn't find a good picture. With that said, I found one very promising library. It works for small projects that don't use TypeScript and Webpack. I think there's a real opportunity here to build more visual tooling. But I told you I'd focus on things we can use today. So we're going to move forward. So at the bottom of our ladder, we can think of our nodes as variables. We're going to draw some data flow graphs. So the best example that I came across for this is the Observable Notebook, which if you haven't seen it before, is like this wonderful union of a Jupyter Notebook and Excel. So like Excel, if you update some cell, you don't need to rerun its children. They'll rerun automatically. However, those cell relationships are not obvious just from reading the notebook. So because Observable was made by Mike Bostock, who created a data visualization library, he made himself a visual debugging tool that you can plug any observable notebook into, and you can see the data flow graph for any one of these notebooks. Every oval is a cell, and this graph makes those cell relationships very clear. So when people ask for help in the forums, he sometimes pipes their notebook into this visualizer and shares a screenshot to help them solve the problem. But back in React land, so reselect is a library frequently used together with Redux. Each one of our functions consumes state as an argument and derives some new state for us. And when you have a piece of, if you have a selector that depends on other selectors, it can be tricky to know what is the downstream effect of updating some high-level selector. And reselect devtools makes that very easy for us. So what it looks like is something a lot like Redux devtools. It's the same diagram that we saw on the previous slide with 3 extra features that we haven't seen in other tools yet. One is that if we click on a node, we've highlighted the ancestors and the descendants. The second is that we can inspect the values at runtime rather than using console logs in our code. And lastly, we can actually count how many times each one of those functions has rerun. So I encourage you to check this out. So now we're almost out of our ladder. I had to make a brief mention of state machines because it's really special in the visual tooling that it enables. So state machines are a model for computation where a system can be represented as a list of states and a list of transitions for how you can move between those states. This is a state machine for a traffic light. So we can write some JSON-like code on the right, and we generate the picture on the left automatically. And then you can take this diagram to your PM or your designer and work together to handle all the edge cases, even if they're not familiar with JavaScript. What's more, it doesn't just have to be a static picture. So you can use a Redux dev tool or an XState dev tool where you can actually interact with something that you can click on produced by your state machine without writing any additional JavaScript code. And just in case this JSON-like syntax is too verbose, there's a tool from the design community called sketch.systems where you can write something that looks a lot like YAML, so we've done away with our curly braces, and you can use that to prototype and similarly get another interactive diagram. There are many tools we haven't gotten to yet, but I'll pause our tour. And for this last section, I've picked out a few ideas that we could apply to the visualizations we've already seen. And they're based on challenges I encountered while I was clicking around some of the tools that we saw earlier and thinking about why it is that I'm not using them in prod yet. So the first of these is the Hairball problem. We're not the first space to have this issue with large dependency graphs. In other fields, something they do is they come up with new layouts, but they're operating on a different order of magnitude. I think that unless we do something to manage the busyness of these large diagrams, it's really hard to take them seriously. Because an automated output sounds good on paper, but if your visualization is not interpretable, it's not much better than not having anything at all. So, as is a theme, I'm addressing this issue by changing the question. Rather than asking, how can I see everything, we're going to ask, which parts do I actually need to see right now? So once again, taking a page from the world of cartography, we can use the idea of progressive reveal of information. Here we have 4 panels, all showing Boston, gradually zooming into where we are. At each level of zoom, we get different levels of detail. At the top level, you can barely see where the states are. As you get closer and closer, we add state labels, we add highways, we add street labels, and this progressive approach prevents us from overwhelming our users as quickly. So an academic way to talk about this pattern is the information-seeking mantra coined by Ben Schneiderman in 1996. It has 3 parts: overview first, zoom and filter, and details on demand. You've probably already noticed it in the apps that you use today. For this talk, I took each one of those steps and prepared a small Electron app to illustrate the small ways in which we could apply these to the Madge File Dependency Explorer. Electron is a library for making cross-platform apps, so whether you're on Mac, Windows, or Linux, you should be able to try this out. I applied it to 2 open source code bases that I've been in recently. One's for network analysis and one's called Interact. So this first view is the overview. I took the Madge tree, and my first wish really was just to be able to click on the diagram that we saw before. So that's what I did. I took a graph visualization library. I removed the labels because I felt I didn't need that detail yet, but we can toggle them back if we need them. I also added colors to separate our root nodes from our leaf nodes, since finding the entry point to your project is very important in a new code base. The second idea that I tried was adding the ability to filter. So when you're clicking around the graph, if you find a branch that turns out to be not relevant to your search, such as your test fixtures or the documentation folder, you can remove those very quickly. There's both a heavy prune that lets you remove a whole folder or a light prune that lets you remove a single file. In case you get prune happy and remove everything too quickly, every one of your clicks generates a regular expression which goes into a menu that you can either edit or refine. If you didn't actually need to do the direct manipulation thing, you could also skip straight to the regular expression list and apply your filters directly. One nice benefit of filtering is that it enables you to apply layouts that wouldn't have made any sense before. So for example, a hierarchical layout which puts your probable entry points at the top and you can follow control flow going down. This becomes feasible once we take the large tree that we saw at the beginning and pruned it down to something smaller. For the last stage of the mantra, I focused on details about the individual nodes. So here I made it so that clicking on any individual node will highlight the neighbors that are 1 degree away, whether they're parents or children. But you could expand this to n degrees if you felt it was relevant. I also made it so that you can navigate using the mini-map on the right or your main view on the left. However, the metadata that we show for details on demand doesn't have to be graph related. Any command line tool that gets metadata about a file could potentially be used. So just as a proof of concept, I get all the recent commits for a file and group them by author, and I sorted them by recency. And a use case for this might be, you enter a new feature and you're trying to figure out who might be most knowledgeable about these files if you're not able to ask somebody for some reason. The second idea I wanted to explore came from the question of having a map but not knowing what exactly to use it for. And for this, I leaned on an idea from architecture. Wayfinding refers to the set of techniques that people use to figure out both where they are and where they need to go. Hospitals, airports, and other public spaces are frequently the subjects for this type of project because people enter them infrequently, they're under time pressure, they may be stressed, and there are very high safety and monetary costs to getting lost. So it's very important that people get to where they need to be. There are several core questions in any wayfinding process, but I focused on selection. The feeling that I had at the end of the previous demo was, I have this automatically generated map. I know how to make it less busy, but I'm not sure what to do with it yet. So there's this idea that maybe we'll add some data and the usefulness of this map might increase, like one of those water grow toys. So once again, this idea is not new. It's what we already do with our geomaps. People don't look at these maps to remember how the states are shaped or what the state boundaries are. You use these diagrams to put other data into a spatial context, whether that's weather data or remembering what flight coverage an airline has. So this is used in other non-front-end tools. Before this, I was a data engineer, and something I really liked about Airflow was the fact that I could see the success status of my jobs right onto a data flow diagram rather than getting a long list of success or fail messages that don't show how those failures relate to each other. We also saw this idea already with the call graph visualization, where each one of those boxes isn't randomly colored, but it's colored by how frequently each function ran or how much of some resource it used, whether it's time or CPU. The reselect tool that we saw actually already does this for our selector functions. So the idea I wanted to share was putting search results on a map, which we already get from Yelp and Google Maps and other geo tools that we like. So I took a search tool, ripgrep, which is a faster grep. I took a visualization of our file system, and I took the results and put them onto the map. So on the left, I've laid out the directory structure of JS Network X's algorithms folder, and let's say I want to see where all the to-dos are. So I made a UI that lets us type in whatever string we want. You could use a regular expression if you need, and you can see exactly where those to-dos are. I also kept our idea from demo 1 of having details on demand. So if you click on a node, you see the lines that showed up inside that file. And we also keep our panning and zooming map-like controls. I think in the future that we might be able to unify these two demos and visualize the relationship between a dependency graph and the file system, but one step at a time. So we've reached the end of our code map journey, and I'd like to recap what we've learned before we go. We started by looking at the reflection model, which is an approach that hybridizes our human design sensibilities with the thoroughness of machines to highlight the sorts of misunderstanding that can lead to a bug. Next, we walk through a zoo of tools that you can use right now, which all build some form of dependency graph at different levels of abstraction. And you can try out all of them with little effort beyond running a script. And lastly, we looked at how the information-seeking mantra combined with sprinkling data onto these diagrams that we've made can make these automatically generated graphics a lot more usable and actionable. I'd like to leave you with a quote about why I feel that developing new kinds of tools is so important. We shape our tools, and thereafter our tools shape us. I don't yet know what that new shape will be, but I'm optimistic that being less lost will make us happier and give us more time to help others find their way. So thank you very much for listening. Please reach out if you'd like to try the demos or have ideas about things we could see.